Okay, I just got cut off there. We had to start this video again, but I'm just going to carry on with what we were doing with these crutches. So we're looking at the equilibrium of forces, and we're looking at the case of someone who has crutches. The weight of the person is 800 newtons. And the question is, how do we find the force in the crutches, which would ultimately be the force exerted up in your armpits, if you want half your body weight on the 1 foot? Okay, so this force of gravity is on your body. The normal force from the ground, your foot on the ground, is half your body weight. So it's half of 800. So that's 400 newtons. Now, the crutch has a force up, which then gets translated up into your armpit. So that's force crutch and force crutch. And we're going to assume that both crutches have the same weight on them. Wouldn't want to do it lopsided. Well, if they're both the same, the two of them together have to be 800 minus 400. They have to be 200 each. So the force of the crutch, each crutch, would be 200 newtons. Okay, so the upward forces would be crutch 1, 200 newtons, crutch 2, 200 newtons, force on your foot, 400 newtons, and then your force of gravity, 800 newtons, and you would be in equilibrium. But we don't usually use crutches completely vertically. We sort of tend to have them off at an angle from our bodies. So what happens if you put now the crutches at an angle? So now crutches are at an angle. So now what's the force in your armpit from these crutches if you start moving the ends of them away from your body? Angle, what is force along the crutch? So do you think it gets bigger or smaller? Well, it turns out it gets bigger. So if you're standing here, once again on one foot, the other foot's hurt, you still want half your body weight on the foot. Now the two crutches still have to make up vertically the extra 400 newtons. So you still have the 400 newtons from your foot, half your body weight. You still have the same force of gravity, 800 newtons. Now the crutch, it still has to support a force vertically of 200 newtons. Okay, so this is a crutch off at an angle now, and 200 newtons. Okay, so this line here, this is your crutch now. Now that's a pretty severe angle, but usually you do have them off at a little bit of an angle. So let's say you're told this angle in here is 20 degrees. Now the force along the crutch is along here, so the hypotenuse, and that's what we want. Now you can see that the force of the crutch, one goes this way and one goes this way. The x components point towards each other and cancel each other out. So this is the force of the crutch. This is F crutch X, and this is F crutch X. They cancel, and it's the two Y components that have to be the 200 and the 200 needed to support your weight. And so if you look at this triangle, F crutch is the hypotenuse. The adjacent side to the 20 degrees is the 200, so it's a cosine that we want. The cosine of 20 would be the F crutch Y, 200 newtons, divided by the force along the crutch. And so the force along the crutch would equal 200 newtons divided by the cosine of 20. This makes it a bigger force. So it's going to be a bigger force into your armpit if you move the legs, the feet of the crutches away from your body. And so this turns out to be 213 newtons. The bigger the angle, the bigger this force has to be. So clearly you want to keep those crutches as close to your feet as possible. Okay, the last example that you're going to see on your assignment is the Russell traction apparatus for femoral fixation. Basically, it's trying to pull your leg out of your hip. Okay, so there's a nice picture in your assignment. Basically, it's the leg that you're analyzing. So your leg, okay, this is your hip joint here. And your leg is attached to a pulley system where we're using the weight of the hanging mass to support your leg in a couple of ways. So if this, let's say this, the force of gravity from this hanging mass is 50 newtons. Okay, so the string's going to go like this. It's going to have a pulley here, a pulley here, and then another pulley over here. So we're going to run the string up over this pulley, around the pulley attached to your foot, around a pulley attached to the ceiling, around another pulley, and then down attached to your leg with some kind of sling thing here. Okay, so these are all pulleys. And these two top ones obviously are hanging from the ceiling. We don't care about the ceiling. We're worried about your leg. Okay, now this 50 newtons, remember it's pulling everywhere. So the 50 newtons is pulling here on that pulley closest to your leg. It's pulling there. And it's pulling here. So it's all the same, 50 newtons. Now the angle between these, let's say it's 40 degrees. Well, let's just say it's theta. Now the force in, we need the force in this string. It doesn't equal 100 because those two 50 Newton forces pulling to the right are at an angle. I did the case where they were exactly parallel to the x direction, in which case it would be 100. But because it's at an angle like that, you have to take components. Now, we have done a problem where we've worked out the force due to the pulley system here on the end of your foot. And those are to the right. Now, this whole system is trying to pull your leg this way. So the reaction is that your hip joint, like your leg doesn't fall off your hip. So your hip must be, all the muscles and tendons and ligaments and things in your hip are keeping your leg attached to your body. So this is the hip joint force on your leg. Now, equally, there's going to be the same force on your hip, but we're not worried about your hip, we're worried about your leg. So this is the hip joint force on your leg. It would have to be left because the force is due to the ropes over here to the right, and everything has to add to 0. So if we were to do a free body diagram for your leg would be a bar. Okay, so this is your leg. It would have this 50 Newton force here, 50 newtons here. It would have 50 newtons up. Now it has a weight. Your leg has a weight, Fg. Pretty heavy if it has cast on it. And then there's F joint. That's the free body diagram, and they all have to add up to 0. So up, down, left, right. So this is theta, and this is theta. This is F is 50 newtons cosine theta. And then this one is 50 newtons cosine theta as well. There's two 50 Newton cosine thetas from those two strings. The vertical 50 sine and 50 sine, they cancel each other out. We don't even have to worry about those. So 50 sine theta and 50 sine theta, they would cancel. So in the x direction, what we have to the right, so if we go right equals left, to the right we have 50 newtons times the cosine of theta plus 50 newtons times the cosine of theta. Those are each string, because this is like that 3-pulley system where we have 2 strings pulling on the end of your foot. That's to the right. Now left, that has to be countered by the joint force in your hip, keeping your leg from being ripped off your body. The up and down, so the y direction, up equals down. Well, up we have that string from that same hanging mass, 50 newtons is up, and then down we have Fg, the weight of your leg. And so you would adjust the masses of everything so that that balanced. Okay, so that's enough for this.